Hello students, here is another video on thermal physics, heat and temperature. So we'll be looking at the different scales of temperature and the different formulas connected with heat that involves heat capacity, conduction, radiation, and we'll also be talking about gas laws, the ideal gas law, from which we get the other gas laws. So that's what we'll be doing in this. There are different scales of temperature: Fahrenheit, Celsius, which is also centigrade, and Kelvin. Okay, so Fahrenheit will never be used here. We will be using Celsius and Kelvin. And it's always good to use Kelvin. Kelvin will always work in all formulas. Celsius will work if a formula involves change in temperature. So to be on the safe side, you just go and always use Kelvin. And it's easy to change from Celsius to Kelvin. Okay, what do? You just add 273 to Celsius to get it in Kelvin. For example, 27 degrees Celsius. Okay, it's 27 plus 273, which gives 300 Kelvin. So it's easy to change from Celsius to Kelvin. So it's my suggestion that you always change it to Kelvin so you won't have any problems in any formulas. But we also need to know how to change from Fahrenheit to Celsius, right? So here, just to start off, you see, the boiling point of water is 212 Fahrenheit. But that's 100 degrees Celsius. So 212 is 100 degrees Celsius. And the melting point of ice or the freezing point of water is 0 degrees Celsius. 0 degrees Celsius. That's the melting point of ice. But that is 32 Fahrenheit. 32 Fahrenheit. So 32 Celsius. So here you have 180 as the difference between 212 and 32, 180 parts. But on the Celsius scale, you only have 100 parts. So 180 parts on the Fahrenheit is equal to the 100 parts on Celsius. And also their starting points are different, 0 and 32. Okay, to cut a long story short, to change from one to the other. So if you want to change from Celsius to Kelvin to Fahrenheit, Celsius to Fahrenheit, that's the first formula that you use. You want to change from Fahrenheit to Celsius, you use the second one. So here are some examples and a big difference. Okay, so if C is 100 degrees Celsius, so you put 100 here, 9 times 100 by 5. Plus 32. So you first multiply by 100 and then you divide by 5 and later you add 32 and you are going to get obviously 212 because we know 100 degrees Celsius is 212 Fahrenheit, right? But if you're trying to change 212 back into Celsius, hey, the very important thing here is do not forget, first you got to subtract 32. You see that? So 212, first subtract 32, that makes it 180, and then multiply by 5, divide by 9, and you would get it as 100 degrees Celsius. So that's a big difference here. So remember, when you change from Fahrenheit to Celsius, remember to first subtract 32, and then multiply by 5, divide by 9, okay? And as already said, to change from Celsius to Kelvin, you just add 273, okay? So that is 27 plus 273 gives 300. So that's how you change from one temperature scale to the other. Here is a WebAssign question. It won't be the same numbers, so it will be helping you to do the WebAssign a lot more faster. So you given 3020 Kelvin, you have to change it into Fahrenheit. All right, so here you're going from Kelvin to Fahrenheit. So first let's change Kelvin to Celsius. All right, 3000 20 Kelvin. What do? Just subtract 273 and then you would get it in Celsius, right? Okay? So 3020 minus 273, and we put it in a calculator, you get 2747 degrees Celsius. And once you get it in Celsius, then you use that formula where F is 9 by 5 C plus 32. So 9 by 5 multiplied with 2747, and then you have 32. And that will give you 4977 Fahrenheit. Consider significant figures, you get 4,980 Fahrenheit. So that's how you do this question. So that's one question from WebAssign, okay? Makes it easy for you. And then we come to the important topic of thermal expansion, where we know that whenever anything is heated, it'll expand. Solids, liquids, gases all expand. Of course, gases expand a lot more than liquids, and liquids expand more than solids. So which one expands the least? If you were listening to me, you would say solids. Okay? And not all solids expand equally. And here you have this diagram of what is a thermostat. A simple thermostat. There are many types of thermostats. And that is a device which is used to keep the temperature constant. Like in the electric iron, when you're ironing clothes, where it automatically switches on and off. So what you have there is actually two different metals. You can see two different metals attached together. And these two have different expansions. So when one expands more than the other. So when you heat it, you see that it bends this way when you heat it. Which means this outer metal expands more than the inside one. Obviously, because isn't the length of the outer one a little bit more than the inner one, yeah? So if you had an electrical connection somewhere here, or so at first in the beginning it would have been making contact, but then this bends and goes away, so that acts like a switch, and that is a thermostat. And when it cools down, when the electrical connection is broken, there is no more electric current, so there's no more heat, and then it cools. When it cools to a particular temperature, it again makes contact, closing the switch. So that's a thermostat. Well, what happens if you cool this thermostat from here? Then what direction will it bend? Remember, it's a law of nature that whatever expands more will contract more. So in this case, this metal will contract more. So since it's going to contract more, it's going to bend this way. You see that? That way, with the metal that contracts more on the inside. Okay, so that means basically it goes in the opposite direction when you cool it, remember. Okay, so all solids expand, in fact, liquids and gases expand. And here is a formula coming up for the change in length of a solid. So what I mean is, if you take a steel rod or an iron or copper rod, whatever you like, take a copper rod and you heat it to a certain temperature. So you know the change in temperature. You know the original length. You want to find how much the length increases. So delta L is the change in length. So that's the expansion. And that depends on three quantities. It depends on the original length, alpha, which is a constant, which is called thermal expansivity, right? Thermal expansivity, and it also depends on the change in temperature. So that's a change in temperature. So if it goes from 10 degrees Celsius to 40 degrees Celsius, well, the change is 30 degrees Celsius, okay? Alpha is a constant which will be given to you. So remember that bigger rods expand more because it also depends on its original length. So that's the formula for expansion of length. But what if you take a plate, like a square plate or a rectangular plate, a metal plate, I mean, and heat it? Now, there's no meaning in saying that its length increases because its area is going to increase, right? its area is going to increase. So the length will increase, the width will also increase. And the formula for change in area is similar, except that alpha is replaced with 2 alpha. Okay? So alpha is the linear expansivity, and you got to multiply it with 2 times alpha. Okay. On the other hand, if it's the volume that you're looking for, the change in volume, like you have a cube, you have a metal cube, and change in volume is what's related to liquids and gases, because there is no meaning in saying that the length of a liquid or length of a gas increased, right? So this final formula for the change in volume is very important. Change in volume, exactly the same format, but instead of 2 alpha, now you'll have 3 alpha. So delta, change in volume, is volume times 3 alpha times gamma, delta T. Sometimes this 3 alpha is called beta. I know. 3 times alpha, beta, and beta is cubical expansivity or volume expansivity. So alpha is, let me hear you, linear expansivity. I heard you loud and clear, thank you. And beta is volume expansivity. Now what's the relation between them? Volume expansivity is 3 times the linear expansivity. Simple, right? Okay. Let's go ahead and see how we can work out a question. So this is about the Washington Monument. It has a height of 170 meter. 170 meter, and that's at 37 degrees Celsius. So when the temperature is 37 degrees Celsius, the height of the Washington Monument is 170 meter. And let's say it's a very cold day and it goes down to, how much is that? Negative 19 degrees Celsius. What would its length be? So 2 things here. Number 1, the monument is going to shrink. Yes, believe it or not, it's going to shrink. And number 2, you notice that the monument is not just made of one kind of material. It's basically limestone. But we assume that it's made of marble, because there's also marble inside. So we will be using the expansivity of marble there. So that's the alpha of marble, which is, yeah, your textbook gives a different value, so I will change it. It's, I think it's, what is that, 6.5? No, 2.5. So alpha for marble is 2.5 times 10 to the negative 6. Notice the unit, it's per Kelvin. To find the change in length, you use this formula. Okay, so you need the original length, which is 170. Alpha is given. Change in temperature. So that'll be negative 19 minus 37, because change is usually final, take away initial. Oh, I hope you took away that, final minus initial. So negative 19 minus 37. All right, so, and that gives negative 56. So multiply all this and find that it's, oh no, that's, I have to change those numbers because I used different alpha. And then finally I used the alpha in the textbook. 0.024 meter. That's 2.4 centimeter, about that big. Yes, the Washington Monument contracts by that much. So you see the contraction expansion is not that much for metals. Okay, you see that. So what is the new height? Well, if you contracted by that much, 170 minus that will give you the new height. I'm sure you understood that. There are so many practical applications of this. If you look at a railroad, you know that there will be gaps between the rails to allow for expansion in summer, right? So you've got to have gaps. Otherwise, when they expand in summer, especially in Texas or wherever, and then it'll buckle, because it won't have space to expand, it'll buckle. There will be all kinds of problems. Another very interesting question is, I've asked this so many times in my life and I've most of the time got wrong answers. All right, you ready? Okay. So let's say you have a metal plate. You have a metal plate and there is a hole in the middle. Okay, you cut out a circular hole, cut it out, remove the material, and you take this metal plate and heat it. All right? Question is, what will happen to the size of the hole? Or what will happen to the diameter of the hole? So metal plate, cut out a circular part and take it out. There's a hole, heat it. What happens? 1, 2, 3, 4, 5. It's a video. I would have given you more time in the actual classroom, but I can only give you like 5 seconds. Most of you are thinking that the size of the hole will decrease, which is the wrong answer. It'll increase. It'll increase. Just believe me. And the proof is, instead of cutting it out, if you had just taken that metal plate and drawn a circle on it with a marker, don't cut it out, just draw a circle. Now heat it, what will happen to the size of that circle? Now everybody will say it'll increase, correct? Same thing happens. So whether there's material inside the hole or not, it's the same thing. So remember that. That's a really difficult question for anybody to answer. So that's about linear expansion. All right, the next thing is actually heating materials. Like if you take a little water in a container and heat it on the stove, well, the temperature of the water goes up. So if you have a bigger quantity of water, you know, it'll take more time for its temperature to go up. Everybody knows that. So the quantity of heat coming into the substance depends on the mass of the substance. It also depends on the substance. Like instead of heating water, if you were heating a piece of copper, wow, copper would get heated up faster, right, than water. So there is a constant involved, and that constant is called specific heat capacity. We'll just call it specific heat. That's a constant represented by the letter C, like I'm drawing here, C. So the quantity of heat that's taken in by a substance depends on the mass, the specific heat, and the change in temperature. Excuse me. Wow. Okay, so that's what is given here. Q is the quantity of heat, M is the mass, delta T is the change in temperature, and C is the specific heat, which will come in there. Okay, so here's the formula. Q is the product of these three quantities: mass, specific heat, and change in temperature. Okay, the mass is in kilograms, specific heat is in joule per kilogram Kelvin. And joule per kilogram Kelvin. Delta T, it could either be in Celsius or Kelvin because change in temperature is the same in both scales, okay? Change in temperature, like 10 degrees Celsius to 40 degrees Celsius. Did I say 10 to 40? Yeah, the change is 30 degrees Celsius. If you change both into Kelvin, you will still get the change as 30 Kelvin because you're adding 273 to both and then take the difference. It's a no-brainer. So in these formulas where you have change in temperature, you could either use Celsius or Kelvin. All right, let's work out one question on this. And before that, let me tell you that water has the highest specific heat. It's 4,186 joules per kilogram Kelvin. So that means if you have 1 kilogram of water and you want to heat it just through 1 Celsius or 1 Kelvin, just a tiny change in temperature, 1 degree Celsius change in temperature, you got to give it 4,186 joules. My goodness, that's big. And just for comparison's sake, if it's copper, it's 385. Sometimes it's given us 390. But look at the difference, 4,186 and 390. This is one of the reasons why the human body temperature doesn't go up that fast, because 75% of us is what? 75% of women is water. That applies to everybody. And that's also another reason why even in a hot summer, you can jump into a swimming pool in Texas because the temperature of water will not go up so fast. Oh, that's again why You could use water as a coolant in the radiators. In fact, you just add a little antifreeze to that. I don't even know why we need antifreeze in Texas, but you could basically, in third world countries, you use water. It leads to corrosion and all that, so it's not advisable, but it's the coolant that you buy is basically, most of it is water, okay? All right, so here is a question. So you have what? 0.220 kilogram of something, I don't know what, is heated from 20 degrees Celsius to 48.1 degrees Celsius. Okay, and so you're heating it and you're adding 4.95 kilojoules. Oh, be careful. Kilo is 1,000, so be careful. So that's Q. You've given 4.95 kilojoules, that's Q. And then you have this mass. You have to calculate the specific heat capacity, okay? And you got to get it in joules per kilogram Celsius or kilogram Kelvin. Both are the same, change is the same. I told you that, so yeah. So the mass is 0.220 kilogram. You have the change in temperature if you take the difference. And then you have the Q. So it's pretty simple. Just use that formula. Q is MC delta T. Remember, changed the kilojoules into joules. Got 4,950. Mass is 0.220. C is what you got to find. C is the symbol for specific heat capacity, right? And there it is. You will get the specific heat capacity as coming up. Yeah, when you divide, you get 801 joule per kilogram Celsius. That's how you do it. Simple, quite simple. So this formula can be applied both in heating and cooling. Okay, remember that. Whether you're heating or cooling, this formula is applicable. In heating, the substance is absorbing heat, and in cooling, yeah, you got it. It's losing heat, right? Very good. So that's something else now. Okay. There is another formula that comes in, but the context is if you take a block of ice, a big block of ice, can you imagine that? Okay, and you make a cavity in it and put a thermometer. I don't know why you would do it, but just do it. Okay, put a thermometer and heat the block of ice until all of the ice has melted. The temperature shown by the thermometer will not change. Wow, aren't you heating it? Yes, you are. So why isn't the thermometer showing a change in temperature? Well, because the substance is not absorbing heat. No, that's not right. The substance is absorbing heat, but it is using it to melt. That's a change of phase, P-H-A-S-E, phase. So whenever there's a change of phase, like the melting of ice or the boiling of water, anything, any change of phase, the temperature won't or will not increase until all of it is melted. So to calculate the quantity of heat used in this case, you have to use the formula M times L. Now what is L? It's a constant. I know, too many constants. It's called the latent heat. The word latent means hidden, so it's hidden to the eyes of the thermometer. Oh, that's the story anyway. So you'll be given the latent heat and the mass. You multiply them, you will get the quantity of heat required to melt it, or to, if you're boiling water, to change it from water to steam. But so the latent heat of ice is different from the latent heat of steam. Which one do you think is going to be bigger? If you take a piece of ice and keep it in the room, it'll melt all by itself quickly. It'll be gone. But it'll take a long time for water in a container to become water vapor. So you know what I'm trying to say. Latent heat of vaporization of steam. Did I say that? Yeah, I said latent heat of vaporization. That means to make it a vapor. The other one is called latent heat of fusion. Fusion means melting. Vaporization means changing it from liquid to gas. Okay. So the latent heat of vaporization is going to be bigger than the latent heat of fusion. So M is the mass, must be in kilograms, and latent heat is going to be in joule per kilogram. Yes, latent heat is in joule per kilogram. So why don't we do another problem just to show you how to multiply two numbers? Okay, no. Remember, mass should be in kilograms, okay? So okay, let's move this fast. What is the heat required? No, that's not fast. Heat required to melt 0.800 kilogram. It's already given kilogram of ice and then raise its temperature. What? So first you have to melt it and then raise the temperature to 31 degrees Celsius. So there are two processes involved here. Number one, you're melting it. So that's a change of phase. So which formula do you use? Do you use MC delta T? You can't, because there's no delta T, remember? Until all of it is melted, there's no delta T. So whenever there's a change in phase, you always use mass times latent heat. So that's what we will do first. So heat required to melt it. So that's mass times latent heat. And the mass is given. Latent heat will be given. Okay, I have not put it there. See, sometimes the textbook uses it as 3.36. I think your text uses 3.36, so be careful. 3.36 times 10 to the 5 will give you a little different answer, obviously. So that's a lot. Did you notice that the latent heat is a lot? That's a lot of heat that 1 kilogram of ice requires to get changed into water. So that's the first step. And then once the ice becomes water, what is its temperature? So ice at 0 degrees Celsius. Well, how do I know it's at 0? Because that's the melting point of ice. Nobody needs to tell you that. Melting point of ice is 0 degrees Celsius. So now ice at 0 degrees Celsius has changed into water at 0 degrees Celsius. So now you're dealing with water. And you got to change the temperature of water from 0 to 31. So that's heating. It's not a change of phase. So you use MC delta T. Is that clear? Yeah. When you heat it, MC delta T. When there is a change of phase, is mass times latent heat. So heat required, MC delta T, the mass is going to be the same, 0.800, because if you melt 0.8 kilogram of ice, you're going to get 0.8 kilogram of water, obviously. And that's the specific heat of water, 4,186, and times 31 minus 0. You know where the 0 came from, right? So you got that second process, and then add the two to get the total heat required. So first, use mass times latent heat, then use MC delta T, because first it's a phase change and then it's just heating. And then you add these two big numbers and you are going to get a bigger number, okay? So you get 3.7 times 10 to the 5 joules. So that's how you do this. Okay, here's another question that just shows you that mechanical energy can be... what am I doing? Okay, mechanical energy. When I rub my hands together, isn't that work is being done? Mechanical energy. And what happens? Heat is being produced. So mechanical energy can be converted into heat. You can warm yourself up, in case you didn't know, on a cold day by doing that, okay? So here, hands are being rubbed 20 times at a distance of 7.50 centimeter. Oh, you move it 7.50 centimeter, 20 times, okay? And there is friction, obviously, which is why heat is produced, friction is given. What is the temperature increase? And the specific heat of the tissue is given because, and we all assume that no heat is lost to the atmosphere. So the tissue here, the specific heat is 3,504.6 joule per kilogram Kelvin. So first you have to find out how much work is done. And then we assume that all of this work, which is going to be in joules, is converted into heat, which is not real, but just assume, will be almost true. how do you find work? Work is the product of force and... Did anybody say it? Oh, distance. Force times distance. The distance must be in meter. So if you multiply the force and the distance in meters, you will get the work. But that's the work done just when you rub it one time. So you'll have to multiply that with what? 20. So let's do it. So that once you get that work, you know that's Q, because we are assuming that all of that work is converted into heat. So that's the quantity of heat. So you get 75 joules, and after that use Q is equal to, some people call it MCAT. That's an easy way to remember, MCAT, MC delta T. Okay, so mass is... oh, and I forgot to tell you that the mass of the tissue involved is given. It's only that I forgot to write it down. So it'll be given. You need not approximate that. You can't. So the mass is given there. And so the specific heat times change in temperature. We're looking for the change in temperature. Let me slow this down. So when you do that, you get 0.214 degrees Celsius. Hey, just remember, I'm really bored that I can't see my students, so I'm like trying to keep myself awake by presenting it this way. That's all, because otherwise, why should I waste time? Anyway, I started saying it, so let me say it. Working at your computer day in and day out is boring. That's not the word, but it's boring without seeing human beings, students who can ask questions and so on, but we got to do it, okay? So that's how you do that. And then this just shows phase change. In a solid, the atoms are just vibrating. In a liquid, they're moving around a little bit, but in a gas, they're like freedom defined. They're just moving. So that's what that shows. And that's why to change a solid into a liquid, you need to break those molecular bonds that give it a particular shape and then separate them. That's why you need that latent heat. That should make sense. Okay. And here we have, what do we have here? Let's see. Oh, this is a problem that we had done, something like we had done. So you have 3 kilograms of ice at 0 degrees Celsius. And you got to change it into water at 20 degrees Celsius. Didn't we do this? We did. So what you do is first find the heat required for the phase change and mass times the latent heat. See, now the latent heat is 3.36. Once you get that, then you have to go from 0 degrees Celsius to 20. So you see that right there. So we did this. I'm not going to take too much time on that. And then you got to add up both of those numbers, these two numbers, to get the total quantity of heat. These questions are going to be important because you're going to have them on your final exam. Did I say that loudly? Okay, I did. So here is a graph that represents phase changes. We can look at this in a minute. Here you have change in heat or heat. It's supposed to be in joule per kilogram, but there's another unit called calorie, so that's given in calorie per gram. Pretend that you've not even seen it, okay? So you have Q, and then on the y-axis you have temperature. What's important is to notice that here you started with ice at negative 20 degrees Celsius. Will it melt when you start heating it? No. Ice will only melt when the temperature reaches 0 degrees Celsius. So first, ice gets heated. And once it reaches 0 degrees Celsius, you notice this horizontal part, there is no change in temperature. So that's why ice and water. So until the entire melting process is completed, there is no change in temperature. And then if you continue heating, the temperature begins to go up until what? 100 degrees Celsius, when water begins to boil. That's right. Once water begins to boil, you can keep on heating. The temperature is not going to change. Why? Because it's changing into steam. And once all of the water has changed into steam, if you have enough persistence and patience and continue heating it, you can get superheated steam. Oh, so steam won't be at 100 degrees Celsius. It will be like 120 degrees Celsius. Where is that important? Where is that used? In the steam engine. Yes, in a steam engine, steam above 100 degrees Celsius is called. So because you want to pack more energy into it, so you produce steam and then heat it again so it has more energy in it, and then you change that heat into mechanical energy, and that's how the first engine started working. Isn't that interesting? The steam engine. We'll talk about this in thermodynamics. We'll wait till there. So that's about phase changes. All right, so this could be interesting, because in winter, in order to protect small plants, you can cover them with bed sheets, old bed sheets or something. But how do you protect big, tall trees? You can't cover them. So what farmers do is they spray water over it. Yeah, you heard me. They spray water over it. How does that work? Because the temperature is below 0 degrees Celsius, as soon as you spray water, it freezes into ice, and the ice now behaves like a blanket. A blanket. That means the heat will not go through the ice. So here we are segueing into what is called thermal conductivity, because the blanket doesn't, ice, which is the blanket here, will not allow the heat to escape from the tree, so the tree will remain warm. That's really strange, correct? Whoever thought about it. But that's exactly what they do. So look at this and read. The ice on these trees release large amounts of energy when it froze, helping to prevent the temperature of the trees from dropping below 0 degrees Celsius. Water is intentionally sprayed. Oh, I told you. Okay. It's intentionally sprayed. Then you have materials that can go from solid to vapor directly. That's called what? Sublimation. In case you have heard about it, sublimation. And then we come to the final, not the final, there's one more. We talk about transmission of heat. So a transfer of heat. There are three ways: conduction, convection, radiation. So first let us look at conduction. Right? The picture here actually shows convection. Convection is when, if anything becomes hot, like air becomes hot, its density decreases and it rises up. So the cooler air comes down while the hot air or the warm air goes up. So that happens in our homes, but it also is very important, happens in the atmosphere all the time. Why is that important? Because the heat from the sun beats down on the ground and the air in contact with the ground becomes very hot. If it had not risen up, we would have all died in under a minute. Believe me, that doesn't happen. Because as soon as the air becomes warm or hot, it rises and goes to the top of the atmosphere. The cooler air comes down. So that process is called convection. So in convection, the materials actually move, taking the heat with them. That's convection. No particular formulas, so I've already told you that. But when we come to conduction, conduction usually happens in solids. Solids. So you put one end of a copper rod in fire, hold the other end in your hand. Heat is going to reach your hand after some time. So that's conduction. So in conduction, this reminds us, like you see the insulation used in the walls of the home actually keeps the home warm or cold, depending on the season. Okay? So it's an insulator. And you know why it's an insulator? Because it has air pockets in it. You know that if you wear two thin shirts, like thin two shirts, there's going to be a layer of air trapped between them. And that air is a bad conductor. Remember? So that's why wearing a jacket in winter helps you. It's like you have two, and so you have air trapped. That's why wool, by its nature, has a lot of air pockets. Oh, that's why birds fluff up their feathers in winter. Have you seen that? They do the dance and fill it with air. They do not know physics, but the air pockets keep the heat from escaping. And that's why we have two glass panes, double window panes. So there is air. You need not really fill it with argon or something. They're cheating us. Just air will do. Because the air trapped between the two glass panes will hold the heat inside or outside. Okay? So that's why, oh God, man, examples keep popping up in my head. The attic is so important. Nobody can go up into the attic in summer, right? You can't, and you should not if you want to be alive. But the existence of the attic is actually the existence of a big, huge column of air, volume of air, that prevents the heat from coming down into the house below where we are watching TV and we want to be comfortable, okay? Or studying physics, let me be honest. So wherever you have air trapped air, you know what I mean by trapped air? Well, it can't move. Trapped between the window panes or trapped in the wool. So when you have trapped air, convection is not possible. I said convection is not possible. And so conduction-wise, air is a bad conductor. Air is a bad conductor. Okay. So here's the formula for conduction. Q by T is Ka T2 minus T1 by D. I wanted to write that clearly. Okay. Q by T is Ka. So you see that diagram. T2 is the hot temperature, T1 is the cold. So heat is flowing from the hot to the cold. A, look at this. A is the area of cross-section. Okay? The area of cross-section. It's not the whole surface area. It's just the cross-sectional area. And D is the length of the rod. It's the distance, that's why. K is another constant. I know, another constant coming in. It's called thermal conductivity. Thermal conductivity. It's different for different materials. Metals are good conductors. I just remembered, if you take a knife, hold it by the wooden or the plastic handle, you don't feel that cold in winter or any time actually. But if you hold the knife, the metal part, you feel cold. You know why? The metal is a good conductor. As soon as you touched, the heat from that part of your body was taken away by the metal because it was a good conductor. But when you hold the handle, that's an insulator. So it doesn't carry away the heat from your fingers. Okay, so that's what I mean. That's why carpets are good. It keeps you warm. You understood? As opposed to stepping on tile. Have you ever sat on a steel chair? Sit on a steel chair, and if you're not properly clothed, you feel it. Feel it. Okay. Because metals are good conductors. Okay. So that's convection. I think I explained it. Hot air rises, cooler air sinks, and that's where you could have a gravity furnace, which is working with, it's kept down below. You don't need a fan now because it rises. Usually, in our homes, we have the furnace on top. So that's why you need a fan to blow the hot air down. I hope you get that. Because hot air will refuse to come down. Just want to say that. So you have to blow it down. But you have the furnace below, then you need to blow it. So that's a gravity furnace. Okay. Well, I talked about all that. And let's do a problem on conduction now. Here is a problem. No, this is the formula for radiation, but I'll come to that later. Okay. All right, here is the problem on conduction. Calculate the rate of heat conduction in watts through house walls that are 15 centimeters thick, about that much, and that have an average thermal conductivity twice that of glass wall. So K is given. Assume there are no windows or doors, so you only have that brick. The surface area of the walls is 140 meters squared. Inside surface is at 20.5. The outside is at 5. Is it summer or winter? I mean, not now, but in the problem. I think it's winter because the outside surface is at 5. So heat is escaping from the room to the outside through the brick walls. So we have all the quantities, and remember K will be given. So Q by T, that's a formula, Ka T2 minus T1 by D. T2 is the higher temperature, remember that? T1 is the lower. And what are you asked to find? You're asked to find the rate of heat conduction. What does that mean? The heat conducted per second. So remember that this T is time in seconds. So rate means heat escaping in 1 second. So when you substitute all that, you get 0.084 times 140, that's the area. And then you have T2 minus T1. Oh, why didn't I change into Kelvin? Because it's in Celsius, change will be the same, right? Okay, change will be the same. So that's why I kept it in Celsius. When you do that, you get 1215.2. Considering sig figures, it's going to be 1220 watts. So that's how you do that problem. 1220 watts. All right, next we have to talk about radiation. Radiation is another process of transfer of heat, and it's basically the process by means of which we get the solar heat on the earth. Because you know that there is miles and miles, in fact millions of miles of space where there is no material, and heat and light both travel through space via radiation. So radiation does not require a material medium. Okay, it can go through vacuum, it can go through space. But radiation from an object depends on its temperature. So if an object is warmer or more hot at a higher temperature, it will radiate more. Radiation also depends on the area of the surface. So if you have like a hot cup of coffee and you want to cool it faster, you can pour it into a flat container which will spread it out and kind of make the surface area bigger. Okay, like pour it into the saucer. So radiation depends on the temperature, it depends on the surface area, and it also depends on the nature of the surface. If it's a black object, it will radiate more than a white polished object. So in fact, the radiation of a black object is taken as the standard, is taken as 1 or 100%, and the radiation of a white polished surface is taken as 0. So to say that a white polished surface does not radiate heat at all, while a black surface radiates a maximum heat. So you will see all that coming up in this formula, where again Q is the heat radiated in T seconds. So you have that formula right there. And here Q is the quantity of heat radiated in T seconds, like I said. E is emissivity or emissive power. Which is 1 for a black surface and 0 for a white polished surface. That's E. A is the surface area. T is the temperature. Remember, here the temperature has got to be in Kelvin. Can't be in Celsius. It has to be in Kelvin. And it is raised to the power 4. Sigma is a constant. It's called Stephan's constant. Stephan's constant, S-T-E-F-A-N, Stephan's constant, which is 5.67 times 10 to the negative 8. Big units, watt meter raised to minus 2, Kelvin raised to minus 4. Anyway, that'll be given to you, so you don't have to worry about that. Again, here, emissivity, E. For a black object, a black body, black object, E is 1. And for a white polished object, E is 0. All right, so here is a question. Calculate, no, this is conduction, sorry. So here is the question. At what net rate in kilowatts does heat radiate from a 295 meter square, so that's the area, black roof, so it's black, so E is 1, on a night when the roof's temperature is 27 degrees Celsius and the surrounding temperature is 12 degrees Celsius. So it's not only the temperature of the object, but also the temperature of the surroundings in which it is kept that affects how much it radiates. Okay, so the emissivity of the roof, although it's black, it's given as 0.9, see? So if it's given, you got to use it. So the formula changes a little bit because of the surrounding temperature. You got to have minus fourth power of the surrounding temperature, you will see that. Also remember, you have to change Celsius into Kelvin. So at what net rate means how much per second, right? Per second. So it's, here is the formula. Q by T is E sigma A. Now you got T1 raised to 4 minus T naught raised to 4. The T naught is the surrounding temperature. So E is 0.9. The area, which is surface area, is 295. Sigma, more accurately, is 5.669, so I'm using that, times 10 to the negative 8. And then you have 300 raised to 4 minus 285 raised to 4, which is what you get when you change the Celsius into Kelvin. Okay, so you got to be careful when you do these calculations. Here it's raised to 4, something raised to 4 minus 285 raised to 4, so you got to be careful. Do that part first and then multiply with the other numbers, and you will get the answer. It's 22,600 watts, but you're required to give it in kilowatts, so divide that by 1,000. That gives you 22.6 kilowatts. That's how you do these problems. So in some cases, the surrounding temperature will not be given. If it's not given, you don't have to worry about it. Just take T naught as 0, okay? 0 raised to 4 is 0. So don't, if nothing is mentioned about the surrounding temperature, just leave that T naught as 0. Okay. Here we come to the next topic, which is the ideal gas equation. In the ideal gas equation, you have pressure, volume, temperature related there, pressure, volume, temperature, and you have the gas constant. Okay, the gas constant, caps R. N is the number of moles. We're going to talk about that, number of moles. Now, pressure has to be in pascals. Volume has got to be in meter cube. Number is just a number. It could be 1, less than 1, or 10, whatever. It's a number, has no units. Here is the universal gas constant, which is 8.314 joule per mole Kelvin. Joule for each mole for each Kelvin. T, again, temperature must be in Kelvin, okay, must be in Kelvin. Now, to give you an idea of what moles means, the molecular weight of a gas expressed in grams gives you the number of grams that will be in 1 mole. Okay. Oxygen has a molecular weight of 32. So if you take 32 grams of oxygen, that's 1 mole of oxygen. Okay? How do we get 32? Because it's O2. Every molecule of oxygen has 2 atoms. All right? So atomic number is 16. Don't be confused. But since there are 2 atoms in every molecule, that's why you get 32. So if you take nitrogen, on the other hand, the atomic number is 14. Again, it's N2, so it's 28 grams in 1 mole. But we can't put it in grams, so you got to put it as kilograms, so divide by 1,000. I think I'm going to write that down here and show you. But before that, you know, if you keep all the terms on the right side are constant. So let's say you keep a gas at constant temperature. And you know that N and R are already constant. So if you don't allow the gas to escape or more gas to come in, then you have fixed the number of moles. R is a constant anyways, T, if you fix that, then you can use P1V1 is equal to P2V2. Okay? But on the other hand, if you keep the volume constant, so you are heating a gas in a closed container. If you heat a gas in a closed container, then the volume can increase. In that case, the pressure increases. So in that case, you get pressure by temperature is a constant. So there you would get P1 by T1 is equal to P2 by T2. So that's what you're going to get. P1 by T1 is equal to P2 by T2. Okay? So depending on what's a constant, you can change this equation. Now, moles, I've told you, I'm writing it down. Moles is But you remember, molecular weight in grams, okay? Oxygen, the same examples that I gave you. Oxygen, 32 grams, which is 0.032 kilograms is 1 mole. Nitrogen would be 0.028 kilograms. If it's carbon dioxide, C is 12, oxygen 2 is 32, so 44 grams of carbon dioxide, and so on. You will be given the atomic number or the molecular weight, so you don't have to worry about that. But just know that 1 mole means the molecular weight of the gas in grams. But then when we calculate, we change into kilograms. Okay, so let's do a problem on that. So PV is nRT, and the problem here is I'm going to consider that you have any gas, any particular gas at STP, any particular gas at STP, right? Now what is STP? Standard temperature and pressure. Standard temperature is 273 Kelvin and standard pressure is 1 atm. But we can't use ATM, so you have to remember 1 atm is 101,325. I know, 101,325. So if you have any gas, could be oxygen, nitrogen, carbon dioxide, whatever gas, if you keep it at 273 Kelvin and 1 atm, that's at STP, surely from this equation, all of those gases will have the same volume. Simple, because you kept them at the same pressure, same temperature. These two are already constants. So you only get one chance to get the volume. So let's find that volume. But we'll assume we're dealing with 1 mole. So we put N is equal to 1. So 1 mole of any gas at STP will occupy 22.4 liters. You're going to get that in meter cube. Just a minute. Watch. 1 mole of any gas at STP will occupy the same volume. Okay? So that's the temperature, that's the pressure. We're dealing with 1 mole. Plug it into that formula, rearrange the volume, make the volume the subject, And then N is 1, R is 8.314. Hey, and there is a reason why I'm going fast, because you can always slow down, you can pause the video. So, that's why I'm going fast, because I know you have the ability and control to do all that, all right? You with me? Okay, so when you do that, you calculate, you get 0.0224 meter cube. And I said that's true for any gas. So all gases, 1 mole of any gas at STP will all occupy the same volume. All right, so I think we need to work out one more maybe. Here is, this is a crazy question, because you've got to be careful. When you hear, this question talks about the gauge pressure. Now, to measure the pressure in a tire, we use a gauge, right? Okay, so the pressure that's measured by the gauge is not the total pressure in the tire. It's not the actual pressure. What we are measuring is the pressure over and above the atmospheric pressure. So that's what you mean by gauge pressure. Gauge pressure is just how much it is more than the atmospheric pressure. So if you want the total pressure, if you want the absolute pressure or the total pressure, you got to add the atmospheric pressure. And when you use this gas equation, you have to always work with the total pressure. You cannot use the gauge pressure. So here the gauge pressure in your car tires, that is supposed to be 2.20 times 10 to the power 5. So that's a gauge pressure. So that's not the actual pressure. You've got to add the atmospheric pressure, all right? So that is the gauge pressure. And I think when I did it, I forgot in the beginning, and then I said, wow, what am I doing? So that could happen to anybody. I'm not even keeping a secret, because I was trying to do this fast. You would say, that's why I make mistakes too, because I try to do it fast. Okay, I caught it. All right, let's stop arguing. Look at this. P1 is 2.20 times 10 to the 5. And then I'm like, let's use this formula. P1 by T1 is P2 by T2, right? T1 was given. 35 degrees Celsius, which is 308 Kelvin. And then the temperature drops later to negative 39 Celsius, so that's 234 Kelvin. So you have the two temperatures, and you're asked to find the pressure, P2. So if you go directly and try to do it this way, you're going to get wrong. You get a wrong result. So what you got to do is, not what I'm doing now, I'm letting you see what I did. Okay? So that is a mistake. Because if you do that, you're going to get the wrong result. You're going to get the wrong value. Look, I could have just cut this out, but I'm not going to. I just did this in a rush, and then I remembered. I said 1 ATM is 101325. So I'm going all the way trying to find it. There you go. So now I've gone back and said, hey, let me find the total pressure. Okay, that changes everything. So I have to find the total pressure, P1. I added the atmospheric pressure, 1.01 times 10 to the 5. Once I get that, which is 3.21 times 10 to the 5, now I can use that to work out the final pressure. And so once you get the final pressure, you get 2.41 ATM. But the question asks you, what is their gauge pressure? So now you got the total pressure, final total pressure. You got to subtract the ATM, 1 ATM. So the final answer is definitely, I put it as P sub 2G. So I put it as 2.41 minus 1.0. So that's 1.41 ATM. 1.41 ATM. So that's the final pressure. That's how you do that. Okay? All right, the last question in this section, and this would be like 8th question in the WebAssign. So most of it, calculate the number of moles in the 2.20 liter volume of air in the lungs of the average person. Okay, that is the volume of the lungs of the average person, 2.20 liters. Note, and you have to calculate the number of moles. So little n. Note that the air is at 37 degrees Celsius, which is the body temperature. And the pressure is the atmospheric pressure. So you're given the temperature, you're given the pressure, and you're given the volume, find the number of moles. So straightforward, plug it into the ideal gas equation. All right, temperature must be in Kelvin. So we get 310 Kelvin there. And then the pressure cannot be in ATM. So that's 1 ATM, which is 101.325 pascals. We're looking for the number of moles. The gas constant is 8.314 joule per mole Kelvin. And the volume is given in liters. Oh, we need it in meter cube. 1,000 liters make a meter cube. So divide that by 1,000, you get into meter cube. So 0.00220. Okay. And then you have PV is equal to nRT. So N is PV by RT. And so there is the pressure there, 101.325. The volume is 0.00220. And the universal gas constant is 8.314. And the temperature is 310. So we get 0.0865 moles. 0.0865 moles as the answer. All right, this has been a long video, and I've taken, why should I even tell you? Okay, I've taken just 3 minutes to make the video. Good, that's just a joke. So I've done that. And now, if you really and carefully study these problems and watch without skipping, then you would understand this. And then you know what will happen? Magic will happen. On the final exam, your grade will surprise you. Because I'm going to ask similar questions, not the exact same. So if you really understand the questions on the final exam, you're going to do good. The final exam is 20% of the total grade. So from now on, I'll try to make new videos for these chapters because they're going to be on the final exam. Remember, there are already videos on this and problems worked out and everything. This is extra. Also meant to help you do the WebAssign quickly. I hope you got it. I was just trying to be a little, stress-free in this video, and because I need that. And I hope you enjoyed it too. So why don't you go ahead and like the video and share it so more people in the world can understand, study physics. Go ahead, do that. Bye-bye.